Okay, I'm going to welcome and introduce today's speaker, who is Gijs, who is somehow connected to DOE, but you are not a Fed, right? You're a contractor, is that right? So Gijs is, as it says there, Interim Associate Lab Director in Environment, Biology, and Nuclear Science and Nonproliferation. So the whole federal government, is in chaos. And part of Gijs's job is to bring some order to the local part of DOE at Brookhaven National Laboratory. He came here to be chair of the Environment, Science and Technology Division. Department.
Same idea.
And then has temporarily moved upstairs from there. The important thing to know about Gijs is that he's an atmospheric scientist, spent his career studying surface atmosphere interactions and how such interactions impact climate and weather, often with regard to clouds and cloud cover. And we share some interest in cloud cover in the Arctic, so he has studied things like ice nucleation and mixed phase clouds. Prior to coming to beautiful Long Island, which is like half a year ago, January, he was 13 years at University of Colorado in Boulder through series, where he worked hard in developing technologies for probing the lower part of the atmosphere, in part as chief scientist of the Integrated Remote and In Situ Sensing Program. Gijs did his PhD at University of Wisconsin at Madison, lovely place, and prior to that, an equally lovely place in Ithaca, New York, at Cornell. After his PhD, he was postdoc at Lawrence Berkeley National Lab, and I should stop talking and let him tell us about his interests. And we love to, whenever anyone from B&L is here, we always like to talk about how we can better connect, interact, collaborate, do seminars there and seminars here, and better integrate. So I'm a big fan of that, and Gijs is well connected intellectually to this group. So thanks for coming, and take it away.
All right. Good afternoon, everybody. Thanks for being here. I appreciate that, and I appreciate the invitation to come and present and provide an overview of work that I've been engaged in. Admittedly, this kind of straddles my previous life at the University of Colorado, with a light show and everything. The University of Colorado and my current role at Brookhaven, but we'll talk about that a little bit more. Before I do that, though, I wanted to give a little bit of an introduction to myself, and let's see if we can get the slides to go here. There we go. So as you may have guessed by my name, I'm not originally from the US. I was born in the Netherlands. I'm an immigrant a long time ago. I have nowhere near the accent that my dad does, but that's where I grew up. It does look like that sometimes. I encourage you to visit sometime in the spring when all the flowers are in bloom. My dad, as I mentioned earlier, he was a captain for ships like this, and he sailed around the world delivering primarily steel, but sometimes other things to ports around the world. And as a result of that, he was always very interested in weather, spent a lot of time focused on weather. And when my sisters were born, he kind of determined that being away at sea for months at a time was not the best parental, not the best way to be a parent. And so he decided to ask for a desk job. And what he was offered 3 options. One, to go to Alaska in Anchorage, and he didn't want to do that. One was to go to Port Everglades, and the third one was to manage the port operations on the eastern seaboard. And so that's what he ended up choosing. We moved to Connecticut on an airplane that looked a lot like this. My first ever point of entry to the US was at Kennedy Airport here in 1985. And the reason I'm talking about all this is because this is where my interest in weather really came from. In his role managing the port operations, one of the biggest challenges that he would face is that it costs a lot of money for a ship to be in port and not be actively loading or unloading. And so weather was a huge factor in that. And he was always monitoring weather. When I was a kid, it didn't matter whether it was Game 7 of the NBA Finals, the Weather Channel would get turned on, and I would be very disappointed because I wanted to watch the game. But that's how it would go. And so when I was looking at universities, I looked for programs in atmospheric science. I did come to visit Stony Brook actually at that time. I ended up going to Cornell instead, but I always was really interested in engaging more with Stony Brook along the way. I did that thinking I would be a TV meteorologist, honestly, because that was kind of what I was aware of from a meteorological perspective. I did actually do an internship for, some of you may know who this is because right across the sound, this is Dr. Mel Goldstein. He was working at the time at WTNH Channel 8 in New Haven. And I had a great summer with Dr. Mel as an intern. I learned very quickly I did not want to be a TV meteorologist. It was early mornings. Very early mornings. And, frankly, it just wasn't what I was excited about. And I was really grateful to have the opportunity to have an internship and learn that firsthand. And so my next step was to look for other options. And so the next summer, I took an internship at the Northeast Regional Climate Center, which is at Cornell. And I spent the summer conducting research, writing Python code before it was cool, back in 2002. Haven't touched Python much since, honestly, but I probably should, given where things are going. But that kind of spurred my interest in research. And so I went to the University of Wisconsin, as was mentioned by Shep, and then I ended up very interested in Arctic clouds. This is a very early LiDAR figure from one of the sensors that we deployed to Barrow, Alaska at the time. This is from a campaign called MPACE 2004. And I was in some ways drawn to the Arctic because that's where we had data. But it ended up being a really good thing for me because I became really excited about mixed phase clouds and the science behind them. So from there, I went to Berkeley Lab. That was my first exposure to the national labs. Also, my first exposure to a lot of the Department of Energy research programs, like the ARM program, which supports a lot of atmospheric measurements. I'm sure many of you are familiar with this program. And some of the science that is conducted at the Department of Energy. After spending a couple of years at Berkeley Lab, I was fortunate to find a position at the University of Colorado, as was mentioned. This is, of course, a fantastic environment in which to conduct atmospheric science. There's a ton of work that's done in this location. And it's there that I got really interested in using small robotic aircraft, which is what this talk is going to be about. But I'll talk a little bit more about that as we go along. And I spent 14 years working out the systems and their applications and had a great time. It was a fantastic opportunity to conduct impactful research. One of the other roles that I took on at CU while I was there was as Director of National Laboratory Partnerships for the university. And that kind of brought me back to the labs in some ways. And I was reminded of how much I appreciate the mission focus of the laboratories and the kind of big science problems that they tackle. And so that brought me back here. And that's a long-winded introduction to, I'm back on Long Island now, or as I first started on Long Island in 1985. I'm now working at Brookhaven National Laboratory, and hopefully many of you are familiar with the laboratory. It is a great place to work. There's a lot of good stuff happening there. Because I'm here at Stony Brook, I won't go into the details too much, but I will show this slide because I always show this slide, and it's just highlighting some of the good things that we have going on Long Island. And I think this is a message I like to carry to wherever I go to talk about the work that we do, just because I think people don't always understand Long Island very well. And there's a lot of great stuff here. You guys know this. I mean, you know that we have some great things to explore, but I like to bring that message to the broader community. All right, very quickly, just a little intro to the department that I came to BNL to lead. Not sure why that image is as fuzzy as it is. Hopefully this doesn't impact some of the other slides that we have. The Environmental Science and Technologies Department is focused on fundamental science and primarily the atmosphere, but the environment more broadly. Most of our work at the current time is focused on clouds and precipitation, aerosol processes, and then boundary layer phenomena. This work is applied in a variety of different areas. Weather and climate, of course, is one of those. But in addition to that, particularly right now, we have a lot of focus on the intersection between environment and energy. There are a lot of ways that environment impacts energy demand, energy distribution, energy production. And so this is something that we think about in the work that we do. We also think about national security and community well-being as other drivers for what we do on a daily basis. All right, so getting to the broader theme of this presentation, this is a video that was collected as part of a field campaign in Barbados. I'll talk more about that campaign in a little bit, but I put this video first because I think it provides a really nice perspective on why small robotic aircraft are a great tool for atmospheric science. And just by show of hands, how many of you have ever had a dream that you can fly? And most people have had this dream at some point in their lives, and it's different for different people. My flying dream was always that I was at school and I could take a running start and just kind of glide along the ceiling and be above things, see them from above. But, you know, as an atmospheric scientist, of course, this is a great superpower to think about. And I think this is about as close as it gets to being able to do that from an individual perspective. Of course, we have large research aircraft, which can carry lots of instruments. There were recent campaigns here in the area that did this, and those provide very valuable data sets. But those aircraft tend to move quickly. They tend to cover a lot of distance and a lot of ground, and they can't necessarily look at things the same way that I would like to think about myself looking at something if I could fly, right? And this is much more like that. It's slow moving. It's much smaller in stature, and it's a little bit more local than some of the larger aircraft. Both have their place, but when you watch the video, it feels a lot more like an individual rather than, you know, a mobile laboratory. When I say slow moving, these aircraft tend to fly at about 15 meters per second, which when you look at the spatial scales that you're measuring at those velocities, they really start to get quite small down to centimeter type of resolution. And that's one of the unique aspects that we bring to the table with these aircraft. A little bit on how I got interested in using remotely piloted aircraft or drones or UAVs, whatever you want to call them. They have many names. As I mentioned, when I was in graduate school, I was really interested in mixed phase cloud processes, and I was working along with some others on a review paper on mixed phase clouds. And what I recognized in developing that publication and some of the figures that go along with it, like this one, is that some of the biggest questions that we had about the life cycle of mixed phase clouds required perspectives that we didn't necessarily have. And many of those were away from surface. So thinking about things like turbulence around the cloud base, radiation at cloud top, aerosol properties and processes in the mixed phase cloud layer, maybe not connected to the surface. They required measurements and locations that were difficult to access with the data sets that we historically have had access to. And so I became really interested in thinking about how we can get some of those measurements. And this was a clear potential application for the small aircraft. I'm not the first one to have this idea, not even close. There have been efforts underway since the 70s to deploy smaller remotely piloted aircraft for atmospheric science. And these are just a few examples of the types of aircraft that have been operated around the country and around the world. This has definitely been a process, but I think one thing that I benefited from is timing. And I don't know if any of you read the book Outliers by Malcolm Gladwell, but it's an interesting read if you haven't read it. It talks about, you know, why some people are able to kind of launch in a direction and be successful at something. And I think part of that story in the book, it has to do with luck and timing. And I happened to be interested in this right as there was a bit of a revolution going on in terms of miniaturization, right? You have Steve Jobs, who of course is a very smart person himself, but bringing things like the iPhone to society, that moves the needle when it comes to development of hardware, of software, of sensors, and all the things that are useful for small robotic aircraft. The phone in some ways helped us a lot, GPS, etc., battery technologies. And so the timing of my interests coinciding with this miniaturization revolution was really good for advancing the science that we were pursuing. So I happened to be transitioning to CU right around 2011, which was, I don't know, maybe 3 years or so, 4 years after the first iPhones were coming out and smartphones were becoming more advanced, more popular, and that provided all kinds of opportunities. And I happened to be moving to a location where this idea of using small robotic aircraft for atmospheric science was already being undertaken. This is a figure from a paper by Jack Elston, right as I was transitioning there, about the work that was being conducted at CU to deploy UAS for severe weather research. And you know, my intersection with that group really spurred us to start to explore a much bigger application of these systems. And this is a photograph of one of our first deployments at Lake Point, Alaska, flying the Data Hawk UAV, which you see in the picture there in front of our mobile facility that was deployed there at the time. This was about 2013 that we deployed to that site. In the process, I was able to engage with a lot of different people. We built a small community of practice for UAS operations in Boulder. I won't go through all these individuals, but I always like to acknowledge the fact that it took a lot of effort by a lot of different people to conduct some of the work that I'm going to describe. And we had a lot of good partners along the way as well, including B&L and other national laboratories and many different universities. All right, so as part of this work, I've been privileged to travel around the world and deploy these systems everywhere from about 87 degrees north to Barbados. Nothing in the southern hemisphere yet, but maybe that'll change in the future. We'll see. I won't go through all of these things now, but I did want to share just a few examples off the top before I dive into details from just a limited number of those deployments. Again, this was one of our first projects up in northern Alaska. If anyone here wants to pursue this area of research, I highly recommend starting somewhere other than Alaska. It's a very difficult place to operate, both in terms of environmental conditions, but also things like bears. Paul and I were just talking about bears in Alaska and how they can impact research. And I've seen lots of bears up there, and we had several instances where we had aircraft in the sky and had to kind of abandon them mid-flight because of the fact that there was a bear coming to our site. But a few other examples, we've done work in the Colorado Rockies. This system was equipped with stabilized pyranometers, so we can do albedo surveys with the drones. We've done work in Barbados, in the Rockies, down to Arctic Ocean, Lake Michigan, all over the place. And all these photos, I like this slide, all these photos involve students at some level. I think every person, except for me, if you take me out of those pictures, most of the other people are students at the time of the deployment. A lot of great ways to engage with this type of field deployment. So for today, I'm going to focus on 3 different locations. One is the Southern Great Plains facility, which is in Oklahoma. And the other 2 are field campaigns that happened in Barbados and in Texas. And I'm going to focus primarily on one aircraft, and that is the Raven. It's not this aircraft, but I'll show this video. This is a video that was collected in 2014, maybe. This is the University of Colorado Twister aircraft, which was used for severe weather research. Here we're intercepting a supercell over the Great Plains. It was a fantastic aircraft, super fast, very reliable. We knew exactly how it operated, but it had 2 major challenges. One, it's fragile. It's a composite aircraft. You're operating in a stormy environment. You're going to have hard landings and incidents. And as soon as you had an incident, this aircraft was out, and it took significant repair. The second was it was very difficult to get into the air quickly. Part of that was that it was launched through a car top launch system where the aircraft was on top of the car. The car would be accelerated to about 60 miles an hour on a road, and then the aircraft would lift off the top of the car. As you might imagine, the roads are not always conducive to driving at 60 miles an hour. And so it became difficult sometimes to get this aircraft airborne. And so we started to look at alternatives to this airplane. It's hitting some turbulence here as we're approaching the storm. And what we came up with was a completely different system. This is the Raven. So some of the things that we changed, one is this aircraft is made of fairly robust foam. This is the same kind of foam that's in car bumpers. So it's lightweight, but it's also quite durable. And it's an aircraft that we had a lot more ability to kind of carve up in some ways and install instrumentation on. This whole bay section in the middle is open for instruments of battery. And I'll talk through some of the core instruments that we flew on a regular basis. One is this multi-hole pressure probe on the nose for making wind and turbulence measurements, measured the airflow of the aircraft at different angles. We had a fine wire array on board to measure temperature and airspeed at very high temporal resolution. We have a pitot probe, of course, for airspeed on board. We have up and downward looking IR sensors on board, so we can look at when we're under cloud or when we're flying over surface gradients, coastal gradients, or other temperature gradients. A pair of temperature, pressure, and humidity sensors that are constantly collecting data at high resolution. And then we've also flown this with aerosol sensors like optical spectrometers, things like that. I'll mention really quickly, we also turned all of our aircraft into superheroes, which is fantastic for outreach. This was Winged Wonder, but we worked with an artist in Boulder who was able to provide personalities for all of our systems. The other advancement that we made with this aircraft is we no longer had to accelerate the car to 60 miles an hour. We just used a pneumatic launcher on top of the car itself. And so that means that the aircraft was highly mobile, highly nimble. We could set up and get this into the air in about 5 minutes from the time that we got out of the car to the time that the aircraft was airborne. Normally it would take a little bit more time, but in a storm situation, that was about as fast as we could make it happen. But it means that we could take this all over the country and conduct operations with a fairly small operating footprint. When we developed this aircraft in about 2018, we put a lot of effort into understanding the system and how accurate it was in terms of making measurements to the atmosphere. This is a figure from the deployment at the Southern Great Plains facility where there's a tower and very regular radiosonde launches. Here we're comparing measurements from a variety of different systems, and I apologize, the text is a little small, but there are actually 5 different UAS being operated as part of this intercomparison. And we're comparing against very regular radiosonde launches where we have aircraft spiral up and collect measurements right alongside radiosonde. So you can see, the one-to-one line where things should kind of match up. You never expect these things to be perfect because there's a lot of variability in the atmosphere. You're not measuring the exact part of the atmosphere as the radiosonde. But in general, you see that if you look at the average, things align very well for some of the systems. Some are a little bit off of that line. Winds tend to have more variability in things like pressure, of course, that's expected. That's what you would expect to see. But from this, we can start to have confidence that what we're measuring with the Raven in particular, which is the gold dots there, is representative of what would be measured by a radiosonde in the same environment. We also looked at comparisons relative to the tower at SGP. So here we have time series, high resolution time series from the sonic anemometers that were on the tower versus what was being measured by the Raven. Again, you don't expect these to align perfectly because the Raven is doing transects next to the tower. It's sampling the atmosphere differently than the tower is, but you see in general, things are very well aligned. We have the same amount of variability, even if we're not representing it exactly at the same time. And that becomes really important when we look at things like turbulent fluxes. And so here we're comparing the Raven sensible heat flux here in this figure, to that from the tower. The black dots are from another aircraft. So again, representing as the tower is the sensible heat flux in this environment. Okay, most of the rest of the presentation is going to focus on 2 different field campaigns. The first of these is the atomic campaign. This happened in 2020, right before the pandemic. I was flying home. Well, when I flew out there, everything seemed normal. When I was flying home, everyone at the airport was wearing masks. So we snuck this in there. right at the end. But Atomic was focused on understanding clouds in the tropical Atlantic, and these clouds impact things in a variety of different ways, but primarily you have very significant differences in albedo, and that impacts how much of the solar energy is making its way into the tropical ocean. And so Atomic and sister program Eureka were aimed at understanding the drivers of variability in the tropical trade regime, cumulus clouds. And so we deployed the Raven to Barbados to look primarily at the subcloud layer. And this figure is kind of a nice illustration of all the different parts that go into governing when clouds are or not in place. And so our role in this campaign was to look primarily at the lowest kilometer of the atmosphere, kind of from the surface up to the bottom part of the cloud layer. And that's again what you were seeing in the video earlier on. And so this is not totally new. There have been studies of tropical trade cumulus before. These are a couple of examples from the 70s. But as I hinted at earlier, these are studies from larger research aircraft collecting some very unique initial observations. And these are typically looking at collections of data that cover large areas over the ocean. They look at different cloud regimes in a single flight, right? So you're potentially sampling a regime like this, and then you transfer over a little bit farther and you have a regime that looks different. Whereas our way of doing this was a little bit different, and I'll talk about that here. So we were flying from Barbados. We were not flying from a ship or anything, but we were located on the beach, northeastern Barbados. This is a map of our flight patterns. Generally, we're about 1 kilometer offshore, conducting longer racetracks of a couple of kilometers out over the ocean surface. We would do this every day, 3 flights a day, and we did that for about a month, then a quarter. And so we were collecting statistics at a given location and letting the clouds happen in that location, and focused on a much more local perspective on what was happening in the atmosphere. This is kind of a standard view from our operating location. You can see the cumulus clouds off on the horizon. We've already seen this video, so you have an idea of what the aircraft was doing. But over the course of this campaign, we conducted, and it's been a while, 37 flights, I guess, 37 flights, and that was several hundred flight hours over the course of that time period. And so this was a standard flight where we would take off, we'd climb up to about 1,000 meters altitude to conduct an initial profile, and then we would spend about 10 minutes at a time at different altitudes, stepping our way down. The distribution shows you that we were typically fairly consistent with those altitudes, except cloud-based move around. Right? So this upper leg was focused on the cloud-based environment specifically. That's why you see this kind of bouncing all over the place. But those other legs were at fairly fixed altitudes of 400, 220 meters above the surface. And so we did this so that we can collect statistics at each altitude from which we can calculate fluxes.
Are you flying in cloud from time to time?
We were, yes. Yeah. I will say our system was not set up to make measurements in cloud. And so that was actually a problem for us because the multi-hole probe would plug up with water. But we did fly in cloud. Yeah. So just looking at some of the data from the campaign. Here, we're looking at the momentum flux and friction velocity. You can compare what we're doing relative to some other systems, like a sail drone that was operating offshore. First, if we look at that, what's happening in the near surface layers, this is from 20 meters above the surface, under different cloud regimes and wind regimes, we see that our observations are quite closely aligned with what was measured from the surface from the sail drone. We can look at the relationship between wind and friction velocity. That's as we would expect it to be. But we can also look at things like the near surface latent heat flux and how that is relating to different cloud regimes, and then the sensible heat flux as well, as a function of wind speed and cloud regime. And as we were doing this, there were a few things we were interested in. One is looking at whether there were clear relationships between the surface wind speed and cloud fraction. we do see quite a relationship here. The colors represent the cloud fraction quantities. The green ones are larger cloud fractions, the dark blues are the nearly no clouds. This is similar to what was measured from an offshore ship from the Ronald Brown, which is located a couple hundred miles offshore. And so far, things are aligning pretty well in terms of understanding whether there are drivers related to wind speed. We were also interested in understanding the vertical velocity distributions. And so this is something that we can do relatively uniquely in a localized environment, where we're looking at distributions of vertical velocity from the surface up to cloud base. And for this flight, that's 630 meters. We can see a shift in the distribution in terms of where the mean is located, but also in the width of the distribution. This is all data that is used for evaluating large eddy simulations of these clouds. And we can look at things like the vertical velocity variance, in this case normalized to the turbulence in the atmosphere, to understand how that evolves with height. We look at that relative to the LCL height. And here all the dots are representing our measurements under the different cloud regimes relative to relationships that were derived historically. Again, this thin line here is from the Ronald Brown that was in the offshore environment. The black line is the mean Raven profile, and then you had a couple of historical publications. And when you look at this, you see quite a spread. And one of the things that we were able to determine as part of our deployment is that part of that spread again connects back to the cloud environment that was in place. That's not meant to say that the clouds drive the turbulence or vice versa, but there is a clear separation between these different regimes that we observed. And then we coupled our measurements with those from the French ATR-42 aircraft to look at the momentum fluxes in the subcloud layer. And this is a paper from Louis Nayens that leveraged our data as well as that from the ATR-42 to understand the drivers of momentum transport in the lower atmosphere and how those connect to cloud cover. Again, here we're separating out by cloud regimes. In this paper, it was done by date, so the colors are fairly matched up to what I was showing you earlier. And there's a complex picture here that connects both the surface layers, so the frictional component impacting momentum flux, but also what's happening at the cloud layer itself. All right, the second campaign that I'll give a quick intro to is Tracer. This is a project that BNL was very heavily involved with in Houston. And the objective for Tracer was to look at drivers of convection in coastal Texas. And so the schematic kind of illustrates a lot of the pieces that come into play there. There is very regularly a sea breeze coming on shore at Houston. You have the city itself with an urban heat island effect. You also have many sources of pollution in the area, which drive the aerosol loading in that environment. And so our role with the UAVs in Tracer was to conduct regular surveys of the lower atmosphere in the near coastal zones, over land in this instance, but between the city of Houston and the coastline. And again, we deployed here over the course of 4 months during the summer of 2022, flying 2 weeks per month for that 4-month window. We had another aircraft with us as part of Tracer. This is the University of Oklahoma Copterson 2. OU partnered with us in this effort. This is a neat aircraft. It's actually now available commercially. So if anyone's interested in pursuing UAV operations for meteorological research, OU worked with Internet Systems in Michigan to commercialize this aircraft, and it's now available to anyone who would like to operate it. But this is a small, about this scale quadcopter, not too different from some of the systems that people may play around with themselves, but it's had years of work towards the sensing component. So they have an aspirated sensing package that's been evaluated very thoroughly against kind of standard background observations. And so this is a pretty tested system. In fact, we purchased one at CU after it became commercially available. Just a little bit of an overview of our operations here. This is a map of coastal Texas. City of Houston's up here, Galveston Island here. This is the Galveston Bay and the Gulf of Mexico. We had two different operating sites as part of Tracer. One was here near the Brazoria Wildlife Refuge. The other was at the University of Houston Coastal Center. You see again these long racetracks. I think we flew in Barbados. We did very similar flight patterns as part of Tracer. And this is just an overview of the sampling dates. So you can see those 2-week windows for the different systems. We did our best to cover as much time as possible while also having some overlap and some representative photographs of the environment that we were sampling. So clearly we were not in an urban environment. We were not in Houston itself, but we were able to collect data in that near coastal environment where the sea breeze was happening on a very regular basis. This is again a map of the flight patterns, and the blue line there is from the Raven. See these stepped statistical legs that we were conducting. The red lines of the profiles that the copper sign was running generally on a half-hourly basis, but especially when the sea breeze front was coming through, they would be going every 15 minutes. So just a few perspectives on the sea breeze from the UAVs. These are the flight times for our aircraft. You can see we flew kind of early in the day, middle of the day, and late in the day. Typically, this was pre-sea breeze. This was around the sea breeze frontal passage, and this was in the sea breeze environment. This is a nice example of one day where we had northerly winds in the morning. Each one of these dots is a mean wind direction in this case for one of the flight legs from the Raven. So you can see the morning time. We had northerly wind, which then shifted to a sea breeze environment where during this middle day flight, we had the sea breeze establishing south of low altitudes and still in the background level off. And later in the afternoon, the sea breeze covered the entire profile. I'm showing this because just to give some perspective on how the aircraft is measuring this. If we look at wind roses for these different times at 100 meters, again, this is the morning. Wind directions are kind of all over the place. But as you move throughout the day, you can see a clear focus towards the sea breeze regime happening at Brazoria, that kind of southeasterly flow. And then at the coastal center, things are a little different because there's also the Galveston Bay, which has its own circulations. And you can see that that stands out through the whole day, where you have a northeasterly component to the windrows driving from the Galveston Bay breeze, and then that southeasterly component from the sea breeze. This figure shows the course of a day where we had a sea breeze occurring. In this instance, the background colors are from the compression, so it's interpolated between flights from compression, and each of the dots represents what the Raven was measuring during that time. They weren't at exactly the same location, so some of the differences that you see here are not unexpected, but you see generally, I think they're looking at the same environment. Going from top to bottom, this is the wind direction. You can see the sea breeze setting up really nicely in the afternoon. Wind speed picks up. The boundary layer growth kind of levels out, stops developing. You see a decrease in potential temperature as the sea breeze comes on shore and a shift in the relative humidity as well. So one of the things that I was really interested in as part of this is what happens with turbulence in the sea breeze. And so this is an example of one of the cases. This is that June 23rd case that I was just showing you. This is the figure that was on the right just a second ago. If we look at things like the vertical velocity variance, KE, and then the aerosol concentrations, we see some interesting things. One is that there's a notable increase in the turbulence as the sea breeze front is passing through. But then a little bit of a decrease during the sea breeze when the sea breeze is set up itself. And we'll get into that a little bit more in terms of what's driving the TKE. And yeah, I'll move on from there because I don't want to get lost in the weeds here. And similarly, on the 27th, we had another case. In this case, we didn't have the copper scenes from the background shading, but we had another case where the sea breeze front was very clearly captured in the second flight. With increased turbulence right along the top of that sea breeze front and throughout the sea breeze after it passed through the flight area. So thinking about drivers of this turbulence in the lower atmosphere. If we look at the TK budget terms, the two terms that we're measuring directly with the aircraft are the buoyant and shear driven production of TKE in the lower atmosphere. And so if we look at what's happening with these individual flights, this is the first flight, the pre-sea breeze flight from the 23rd. You can see that in general, you have buoyant production of turbulent kinetic energy in the lower atmosphere, much more so than shear driven production. And that actually intensifies as the sea breeze picks up. That may be a little bit counterintuitive, thinking about what a sea breeze is. You have an acceleration of the wind, so you might expect that there's more shear, but the reality is we were not getting through the entire sea breeze layer during most of those flights. And so this increase in the buoyant production comes as a result of two things. One is that as the sea breeze front passes through, you actually decrease the cloud cover behind the sea breeze front, and so you have a more direct heating of the surface happening, and at the same time you're injecting slightly cooler air over that surface that's forming at the ground, and so that's driving stronger buoyant production of TKE in the lower atmosphere. We see the same thing in the second case. In this instance, we had slightly stronger wind, so you do see some more shear-based production near the surface early on. But as the sea breeze comes in, again, you can see that the buoyant production dominates. You put all these pieces together, you can start to map out what type of convection is in place or what kind of turbulence is in place. So you have stable conditions on the left, forced convection or free convection, and these sea breeze cases are all falling in this kind of free convective regime. A lot of buoyant production and reduced shear-based production of TKE. We can look at this across different conditions, and so we used information from Era 5, I believe this was, to classify different sea breeze regimes. And here we're looking at segregating this into cases where there's a dominant sea breeze, superimposed sea breeze, which is a sea breeze that's sitting on top of a synoptic flow that's also from the southeast, and then instances where you had no southerly flow at all. So here are the criteria that were used for separating out these cases. And if we separate out, going back to the TKE, these different types of conditions, we see that for the sea breeze environment, again, very strongly in this free convective regime. Generally true with the superimposed sea breeze as well, although there we do see more of an impact of shear in the development of TKE, which is not unexpected given that you have a stronger synoptic setup in those instances typically. And then when we look at non-sea breeze cases, we see much more of a mix of producers of turbulence along the sphere. Another thing that we looked at were aerosol properties. So for tracer, we did carry a POPS, which is the optical particle spectrometer that was developed at the NOAA Chemical Sciences Laboratory. This figure shows particle concentrations as a function of wind direction and colored by LCL height. Right, so if we bring the LCL height down, you have less atmosphere through which to mix the particles. You expect higher concentrations. But in instances where you have a deeper boundary layer, you expect that the concentrations would generally be lower. And in most cases, that's true. You see the green dots lower than the blue dots for a wind direction. Some instances, not so much. These are the sea breeze cases, the southerly, southeasterly flow. We haven't fully unpacked why that turns around there, but it's something to think about. We can also look at kind of directionally where pollution tends to be affecting from. Not surprisingly, in Houston, there are some dirty sectors and some clean sectors. When we look to the east, you're looking at a lot of the refining areas along Galveston Bay, a lot of the ship traffic in this environment as well as down here in Freeport and Lake Jackson, there's a lot of industrial activity, and you have some cleaner sections. All right, approaching the end here, a couple of things I wanted to bring up. So one is that the University of Colorado has a community infrastructure and facilities project through NSF. So these systems can all be requested as part of the NSF observing pool. So as people are planning field campaigns, if there is interest in including drones or UAS or any of the things that I've talked about here, it is possible to request these through the National Science Foundation. This is of course separate from what I'm doing now, but I'd still like to advertise that this is a possibility. And that includes the Raven that I talked about quite a lot. It includes the Copperson, as well as some of our surface vehicles that I'm showing here. Please come and talk to me if that's of interest to you. Happy to provide more details and a point of contact. Also, just briefly talk about what we're working to develop at Brookhaven. So BNL historically has had UAS operations. However, primarily those have been focused on the terrestrial ecosystem. So largely using video cameras to look at surface. And this is a picture of one of the drones that BNL flies with this hyperspectral camera to look at different surface characteristics. These systems are quite capable. They're very large quadcopters. They can fly at up to about 77 pounds, which is really substantial for something for a quadcopter like this. And we're working to develop payloads for this, primarily on the aerosol side. So BNL has a lot of expertise in aerosol science. In fact, we already have several miniaturized instruments that have been flown on the tethered balloon system that ARM operates. And we'd like to transition some of those to drone-based operations as well. In addition, we're working towards getting some of these weather-based UAS in place at the lab for future deployments. Another part of this that I haven't really touched upon yet, but that I maybe should mention quickly, is the access to airspace. As you likely know, you can't just go out and fly these things wherever you'd like at any time. And therefore, interacting with the FAA and having a good idea of how to go about requesting permission for flight operations is really important. It's something CU does very, very well. They have a whole library of certificates of authorization to fly many different places in the country. They have some COAs in the Midwest that span hundreds of kilometers for storm casing purposes. BNL has a few COAs as well, including here on Long Island, that extend up to about 1,200 feet above ground level for these systems. But it is a part of the equation. It always comes up in the questions when I talk about it. I don't know, Steve, if your question about flying in cloud was related to airspace or just scientific interest, but sometimes people wonder about these things. All right, so quickly to summarize here, it's a lot of fun. I'll start with that. It's a lot of fun to think about, you know, what I would do if I were able to fly, and if I wanted to sample specific environments, you know, how I would want to do that, and how we can instead send robots to do that for us. These small systems offer a lot of opportunities to provide really detailed measurements of the atmosphere, particularly in areas that may be dangerous to send other systems or other aircraft. We tend to fly these at very low altitudes, in icing environments, near volcanoes, things like this. And it's a great opportunity to collect data where otherwise we might not be able to. University of Colorado has deployed these systems all over the world. There are several groups around the world that do conduct this type of research. I encourage you to seek out information on those if you have interest in pursuing this sort of work. There have been numerous advances recently. There will continue to be advances, particularly I would say things like battery technologies that allow these systems to fly longer and farther. There's also advancement happening in the FAA side of things, on the airspace side. Part 108 is something that's coming out soon, I believe. 107 is the typical operation, the typical regulations that's used for small UAS operations, but 108 allows for easier, not easier, it allows for beyond line of sight operations, essentially. That's been a bottleneck for a long time. Often we can't go beyond where the operator can see the aircraft. I think technology is now allowing us to advance that a little bit. We're working towards having some of these capabilities here at Brookhaven, and it'd be great to partner with any of you from Stony Brook on deploying those systems if there's interest. And I'll say again that the University of Colorado also offers access through the NSF SIF program. So with that, I'll acknowledge some of the funders that have supported this work, and I'm happy to take questions from anyone who has them. So thank you.
Hey, questions? Nice.
Use stresses for that subtropical side.
Yes.
Have you compared it or anybody compared it to Euro 5 stresses?
I have not. I can't say that nobody has, but I have not. So might be interesting to do that. There's different scales, of course, but yeah.
Yes, so in terms of the turbulent kinetic energy, one thing that would be interesting is the cloud top radiative cooling.
Yeah.
Do you have an infrared radiometer facing downward? You mentioned that there is a radiometer facing upward.
Yes, we have both up and downward facing.
Okay.
Yeah, we typically have used the upward facing for this purpose to look at when we're under cloud base or not. One of the things that I have wanted to do for a long time and not had time to do is compile the data from Atomic, where we were flying right at cloud base, to look at the vertical velocity structure right at the cloud edges. As we transition in and out of the subcloud regime, there's always this idea about this subsiding shell.
Right.
And it would be very nice to compile statistics on that based on the clouds that we sampled during that regime, during that deployment. Yes.
With these mixed-phase clouds, are there any opportunities or vehicles that might be able to safely fly all the way through the cloud, not have to worry about icing or other problems?
Yeah, that's a very good question. So icing is a concern, like it is with any other aircraft. We have flown through mixed phase clouds. Typically, the environment above the mixed phase cloud can be quite dry, and so once you're above that cloud, usually you're in decent shape. But again, this is one of those instances where we're okay doing this in certain controlled environments where we know the risk is low and we're flying low-cost aircraft, because we don't have a good perspective on how quickly things are icing up. We typically look at the aircraft performance. So we look at, the throttle settings and stuff like that and how it's doing while it's climbing through the cloud. If we start to see a large increase in the throttle, we know that there's likely icing going on. But it is possible. In terms of de-icing, active de-icing, there were efforts underway, and this is somewhere where technology could be quite helpful. I know there were different coatings that people were looking at, like kind of nano coatings that could be used for UAVs, but I haven't seen a highly successful application of that yet. It could be that I've just missed it. I will also say that some of the kind of commercial systems, particularly on the quadcopter side, have looked at this problem as well. And so there's a company in Switzerland called Mediumatics. They have a hexacopter that they fly. They have heated props. And so because they're wanting to sample up to 5 or 6 kilometers very regularly. And of course, they're wanting to do this in all weather conditions. So they do have a prop heating system to avoid icing and to shed ice as the system is climbing.
Thanks.
Yeah.
So I'm a professor, and that means that I can't just ask a question, that there has to be an introduction.
Please.
So you talked about platforms. My experience with people who own platforms is that they always wish they had something else, something better, however you define that. It's typically you want to be in the sweet spot of cost and ease of operation, capability, payload, and power. So I know what I want as a chemist. I want a bigger airplane than I have had that can, we can put an aerosol mass spectrometer on there and get chemical composition of the aerosols when you're flying through a cloud. We also want the cheapest, dumbest navigation system you can possibly find, meaning a human at the controls. So that's a very different sort of thing. I'm curious about what it is for your personal science you wish you could do with UAVs. What can't you do for various reasons? And what you think the future is? You know, where should people be investing? If you were starting a small company, what would you want to build?
Sure. Yeah, it's a very good question. I'll start by saying that this is a discussion I had many times with my engineering colleagues at CU, who were constantly trying to innovate and advance and move things forward. And I was constantly applying the brakes to that and saying, we have a very good system. We need to just get a lot of measurements with the system we have so we can actually do science with it rather than having a lot of measurements from different systems that we don't know how to interfere. And so that's not to say the system is perfect, but at some point, when you find a system that works well for a given application, my own focus goes towards flying it as much as possible rather than trying to make it better. And I would say in this instance, the Raven is pretty darn good. With a standard payload, you get about 2 hours of flight time. It's very nimble, it's low cost, it's easy to deploy. It checks a lot of boxes. Can it carry everything? No, it definitely can't. However, I would say that flying multiple aircraft is relatively easy with this system. And so if you can distribute the measurements that way, that's an option. If we talk about moving forward, where things should be going, I think one of the biggest hangups has typically been the limitations around how we can fly the aircraft. All for good reason. I'm not trying to argue that the rules that are in place are worthless and shouldn't be there. But I think that pushing technology that would allow for different modes of flight operations, whether that's beyond line of sight, higher altitude, etc., I think opens up a lot of doors. Some of those things are happening. You know, for example, CU has deployed in the last couple of years gliders that are balloon launched up to about 95 kilometers. Or sorry, 95,000 feet, not 95 kilometers. That's too much. 95,000 feet. Balloon launch and then glide back to base. So that some of the instruments that had historically been balloon launched and then lost or been very difficult to recover are now brought right back to you. So things like this, I think, are really ripe for continued innovation. It's not necessarily in the atmospheric science side, but it is in the airspace management, flight reliability, et cetera, side of things. I think that will open up a lot of possibilities. I think that's where the commercial sector is actually putting a lot into it. When we look at companies like Mediamatics, who have spent many, many years developing a system that has developed trust with the Swiss FAA equivalent, right? And starting to do that here locally. They've been flying in North Dakota, for example, for I think a couple of years now. That's the sort of advancement that I would push for, is to be able to get these systems deployed much more broadly, rather than having one system that does one thing very well and try to get more data generally. Steve?
Yeah. Prompted my question about in cloud.
Yeah.
Is your statement that you were using a hot wire for velocity. And we used to use a hot wire for measuring liquid water content because of the heat of evaporation of the drops that are impinging.
Okay.
And one of the issues that one of the surprises maybe that we had quite some years ago was the heterogeneity of clouds. That you look from the ground, you look up, you see, oh, it's a nice uniform stratus layer. Great, we'll just fly in this thing. It's going to be uniform as can be. It's not. You have patches of cloud-free air embedded in this nominally cloud layer. And one of the things we were trying to get our hands on was sort of the spatial dimension of the variability of cloud, non-cloud. And if you get rid of all these instruments that are clogging up because of the cloud, and you just want to look at cloud properties, I think this would be great. You just fly it horizontally through the cloud and you get some dimension, some measure of the spatial dimension of that variation, I think it's gonna be a lot shorter than anybody thinks.
Right. Yeah, it's a very good point. A few things there. One, a lot of interesting cloud seeding, right? And that's somewhere where CU has worked with the UAE to develop a bigger version of the Raven that also carries cloud probes along with aerosol instrumentation, not for seeding, but for detecting seeding conditions that are right for seeding. And so it's not necessarily specific to your scales question. On that front, I think another big question that has come up many times is when is a mixed phase cloud mixed phase? Right? What is the scale of variability in ice with liquid together, and how does that vary in different cloud environments? That's not a question we have good answers for. You know, in terms of the volume that defines mixed phase versus liquid.
Spatial variation and how is it centimeters?
Yeah, exactly. And then this is somewhere where we have attempted to get answers with larger aircraft. But again, the velocity, the speed of the aircraft becomes an issue relative to the sampling rate of the sensors, just because the minimum observable scale or resolvable scale is still pretty big. And so that's something that I think there is an application there and something that would be fun to pursue. But again, coming back to the earlier question about flying in mixed phase cloud for a long time period, that's not something we've solved yet. That'd be great to work towards.
I've been on an manned aircraft, person to aircraft that was flying in mixed phase cloud and was icing up, and you don't want to do that.
No, you don't. And I want to make sure I'm very clear about this. I know we're out of time, but I'm not someone who's advocating for getting rid of large research aircraft. I think they have a very important role in atmospheric science. I think that there are complementary views that can be obtained with these aircraft, but I think we very much need both of those types of systems to answer the questions that we have.
Okay, so that brings conversation to the lunchtime, right? So let's sanitize for one more time.